Hello everyone and welcome back to session 4 of What Data Science Society's course into the Tidyverse. We're going to start with a quick recap of some of the stuff we looked at in the last session. So first off, statistics. So we started off last session by looking at these things called statistics. And these are essentially functions of our data. So taking many data points and collapsing them down into a single value. We saw many useful statistical functions such as mean, median, min, max, and quantile. And this quantile one, that's the least intuitive of these, was used for extracting the quartiles of the data. So splitting your data into 4 parts and extracting 5 numbers that define where those 4 parts start and end. We also saw the range function, which gave the range of our data. But rather than giving a certain number, the actual difference between the biggest and smallest element, it instead gave us both the biggest and the smallest. So we could pass this into the diff function to calculate the difference of that range, which is the typical scientific range we're familiar with. We also had the IQR function for interquartile range, which gave the range between the lower and upper quartile. So a range function that's a bit more robust to outliers. Then we also saw the functions for calculating variance, that is var, and standard deviation of the data, which is SD. The important thing that applied to all these was that whenever our data contained missing values, so these NA values, we had to use na.rm for remove equals true to ignore these missing values. Otherwise, we would be guaranteed to have NA as the result of any of these. We also saw how to perform comparisons and how to string these comparisons together into Boolean expressions using Boolean operators. And so we saw the basic comparisons, less than, greater than, and their equivalence versions. And also we had for equality, this double equals, meaning for checking equality. And we really emphasized the point that you need to be using double equals and not a single equals, because the equals by itself is used for object assignment taken from other languages. We also had exclamation mark equals for not equal to, or this near function, which was the same as equals, but when we might have rounding errors from the way that numbers are stored. So whenever we're checking for equality of decimal data, we want to use the near function. And then we could combine kind of any truth values, so any values created by these comparisons, using the and, or, and not operators. That was the ampersand, vertical bar, and the exclamation mark. And we saw a very nice feature of R is that all of these operations, these comparisons and Boolean operators are vectorized. And so if we had a vector of numbers, we could compare those against each other, or logical vectors, we could apply Boolean operators to those. Okay, and then we use those to work with dplyr, and that is the package in the Tidyverse responsible for data manipulation. And so we saw 5 kind of core dplyr verbs or functions. Those were filter, arrange, select, mutate, and summarize. And respectively, those were used for picking out certain observations, kind of filtering down the rows. Arrange was for reordering our observations. Select was for picking out certain columns. Mutate was for adding or overwriting existing columns. And summarize was for collapsing down our rows into a single summary statistic. And this summarize and mutate, I guess filtered to some extent as well, those worked, or those were more powerful when we combine them together with the group by function. And this changes the scope for any aggregating function, or another word for aggregating functions is statistics. So if we're calculating, say, the mean, by default, that would be the mean of the whole data set. By changing what scope we're grouping at, that mean will act on different sets of data. And then we saw we could combine these all together using the pipe operator, symbol here, have these really elegant pipelines or kind of these data workflows where we didn't have to create temporary variables as we went through. Okay, so today's session is about this thing called tidy data. And this is kind of really at the core of the Tidyverse. That's why it's called the Tidyverse. It centers around this idea called tidy data. And we'll see that this kind of goes beyond what we might colloquially think of as tidy data, just data that's not messy, to actually formally define what it means for a data set to be in tidy format. Let's kind of remind ourselves, where we are on this whole map of data science. And actually, I have a motivating quote taken from Ali Wickham, who's the author of the book Art of Data Science and chief data scientist at our studio. And it is kind of an adaptation or variation of a Tolstoy quote. And it says, tidy data sets are all alike, but every messy data set is messy in its own way. And what this kind of hints at is that in this session, we're going to try and define a very rigorous and standardized format for what is tidy data. And then, so this is called tidy data, it's a consistent format. And then we'll see that everything in the Tidyverse works really well with this. It was quite elegant data analysis and data science abilities. On this map of data science, we're currently here. We import our data, and the first thing we want to do is make sure our data is in a tidy format. Everything else in the Tidyverse, the transformations, so with dplyr, visualizing with ggplot, and any modeling or communication, which we don't get to in this course, it's so much easier if our data is in tidy format. So it may feel like a bit of unnecessary work up front, but kind of this pays off in the long run, where the whole exploration part of our data process becomes a lot simpler. Okay, so we're going to use a package called tidyr for doing this kind of tidy data processing. It's just one more package in the Tidyverse, and even though it's maybe not the most commonly used package in the Tidyverse, definitely the most foundational. Like the Tidyverse would not work without tidyr. And the idea is it allows us to take data sets and transform them. Maybe I should say, it transforms them from one form to another. And so it can take non-tidy data and turn it into what we call tidy data, but we'll define that in a bit. The idea is, once we're in a tidy form, we can spend a lot less time and effort kind of manipulating and visualizing our data, which makes it easier to answer our questions quickly. Okay, so the first thing we need to do is figure out what tidy data is. And we're going to do this through some examples. And we're going to focus on a single data set, but that's going to be represented in different ways. This might seem like a bit of a new idea. The idea you could have a single data set, but represented in multiple different ways. But we'll see here that same data set, like 4 times, but each time we organize it in a different way. And we'll see that some of them are perhaps easier to work with, and some are challenges. And so these data sets contain information, I believe it's about TB cases, in various countries at different times. Each data set has 4 variables: the country we're looking at, what year, what the population was at that time, and how many cases. And from now on, I'm going to assume it's TB, but I might be wrong on that. How many cases of TB that there were. And so only one of these data sets is in tidy format, is tidy data. And all the others have kind of a flaw to them. We can then use tidyr to resolve later in this session. Let's start with this first table. So this is table 1. And this is a very sensible representation of this data. So have 4 kind of bits of information: country, the year, how many cases, and the population. So we have the country is Afghanistan, and in the year 1999, there were 745 TB cases out of this population. That is one format for this data. But it's certainly not the only way of representing this data. Another format might be like this. This is table 2. And here you can see we still have each country in each year, but now we have, rather than a cases and population column, you have a type column giving the type of variable when we're measuring, whether it's the number of cases or the population, and then what the kind of count of that variable is. So see, for Afghanistan in 1999, the number of cases was 745. Afghanistan 1999, the population was this number. So the exact same data is contained in both of these. I could construct this data set from the one on the left, and I could go vice versa. But this is a different way of representing it. And then the question is, which of these is the better representation for working in the Tidyverse? So let's look at another format. So here we have very similar to the first one, but now we combine cases and population into a single column called rate. And here we give the number of cases, slash, and then how big the population was at the time. Again, the exact same data is represented here. I could go forwards and backwards between these formats, but some might be better than others. And then the final format is actually split across 2 tables. So here we have one table for the number of cases, that's 4a, and then another table for B for the number of for the population. Again, exact same data, but now we have columns that make up the years. And then rather than having columns for the variables, we split those across two tables. Okay, so all these represent the same underlying data, but some of these are going to be much easier to use with Tidyverse, or with the Tidyverse, than others. And the one that's the easiest to use is the one in tidy format. And so that's the one we're going to want to use, and we're going to want to know how to take the other ones and convert those into a tidy format. So let's define tidy data. So there's three interrelated rules that make a dataset tidy. So if a dataset satisfies these three rules, and only if it satisfies these three rules, it is considered to be tidy data. The first one is each variable must have its own column. So what is a variable? Well, it's something we can measure about an observation. Actually, let's do this in the other order. This is the order that Andy Wickham defined them. I think starting with number 2 makes more sense. So each observation must have its own row. And so an observation is a thing that we can measure things about. So it's just something in the world which has measurable properties. And so in this case, something we can measure something about is a country in a certain year. And the things we can measure about it are the number of cases and the population. And so you might think that a country is something that we can measure a property about. But a country doesn't have a population. Only a country at a certain time has a population. And so even though it may seem like the actual thing is the country, because that's the physical thing, the thing we can measure things about is a country at a certain time. And so each observation is one of those. And then a variable is any measurable property. So if we have a country at a certain year, well, the name of the country, that's something we can measure. I mean, we're not directly measuring it. It's something that could technically be measured. What year it is that we're looking at. And then things that are actually physically measurable, so the number of cases and the population. Those are the measurable properties of a certain observation. And then the final rule, I guess the simplest of the three, that every value, so every kind of number or piece of data, should be in its own cell. So we don't split data across cells, we don't have two bits of data in the same cell. Visualizing this, we have something like this. So variables going down, each one has their own column, each observation in its own row, and values by themselves. And so I mentioned that these rules are interrelated. And kind of the reason for this is that it's impossible to satisfy just two of these. If you satisfy two, you automatically satisfy the third one. And so because of this interrelation, it's actually possible to distill these rules down to an even simpler set of instructions. So make your data set tidy, put each data set in its own table, so its own table, and then you put each variable in its own column. If you do these two things, then you're guaranteed to satisfy these three things here. So why do we have two different definitions here? It might seem confusing. And the reason is that this definition is much better for making a dataset tidy. So, if our dataset is not tidy, then, either things are split out across across tables, in which case combine them together, or we have variables that, we have columns that aren't variables, in which case we have to resolve that. This is the easy way of looking at things for trying to make our dataset tidy. But when we're trying to look at a dataset and go, why isn't it tidy? Well, then these are simpler instructions, because these give us kind of more reasons, I guess, more flexibility in why a dataset might not be tidy. And so for disproving tidiness, we use something like these. And for making something tidy, we use these. But you're free to use either. Those are just kind of the easier ones for each scenario. And so following these rules, only the first table, table 1, was in tidy format. So we can see each row here is an observation, something we can measure things about. So a country at a certain time, that is an observation. And then the things we can measure is the name of the country, what year we're in, the number of cases, and the population. So the natural question to ask is, with those other non-tidy formats, how can we fix that? How can we make it tidy, look like this data here? So we're going to start by looking at this thing called gathering. And that's going to allow us to solve the problem in table 4. So table 4 was actually split out into two tables. we're just going to look at table 4a to start with. The same applies to 4b, and then we'll see later in the session how we can then combine those two together to get back to table 1. But we're not going to worry about that just yet. So what's the problem with table 4a? It looks something like this, and we have columns 1999 and 2000. So this violates the first rule of tidy data. So the first rule was every variable has to have its own column. And so a variable is something we can measure about our data. Is 1999 a thing we can measure about our data? It's not really. The number of cases, that is something we can measure. And so, the columns we have should be cases. That's something we can measure. 1999, 2000 are not things that we can measure. So yeah, these two columns, these are not variables. And so instead, these actually represent values of the variable column year. So the year is something we can measure about a country in a given year. And so these should actually be values in a column called year. As I mentioned, these rules are interrelated. We can't fail simply one of those. And so as a consequence of failing the first one, also fail the second one, which is each observation has to have its own row. We said observations were a country in a certain year. In this case, we have information about Afghanistan for both years in the same row. So 2 observations are contained in this same row. And so we're going to want to fix this. So we can do this by using a technique called gathering. So we want to, essentially what we want to do is take these non-variable columns and gather them together into a year column. And so the reason we think of this as gathering is, imagine we had more of these columns. We had 1999, 2000, 2001, 2, 3, 4, 5, loads of these columns, and we want to gather those all together into a single column called a year, and then have another column containing the number of cases. So all those columns gather together into 2. And so if you want to describe this operation, we're going to need to specify a few details. The first is what columns we want to gather together. So in this case, it's the columns 1999 and 2000. So more, we want to gather all those together. Then what we want to say is we're going to gather these together into 2 columns. One's going to contain the values that are currently column headers, and the other one's going to contain the values that are in the dataset itself. And so we're first going to need to assign a name to the new variable that's going to store the information in current column headers. And we refer to this as the key. Bit of a confusing name, but the other one's called value, and the value makes sense. So you got to think the value is the one that's kind of clear, the key is just the other one. And so the key is going to be the column representing the values that are currently in the column names. And so in this case, the name of the column we want to create is year, because these values here represent the variable year. The other thing we're going to need to do is to specify what variables is being represented by all of these values inside of the table. Well, these are the number of cases. And so we want to set the value column to be called cases. And so this is seen a bit more clearly in an example. So we take table 4a, we're going to use the pipe here to put that as the first argument here. We could have just put that straight in, but piping makes it a bit clearer. And so then the first thing I said, we want to specify what columns to gather together, and that's the columns 1999 and 2000. And so in this case, we have to use backticks around the numbers. If these columns had kind of text names, so letter names that were made of letters, then we wouldn't need the backticks. We need these because by default, when we use a number in a lot of Tidyverse functions, R will interpret these as the 1999th column and the 2000th column. It's going to give us an error when we only have 3 columns in the dataset. Instead, we use backticks to say, no, we really mean a column name here. Those are the ones we want to gather together. And then the key is the name of the column for which its values are currently contained in the column names. So column names have the values 1999, 2000, and these currently, these are values of the variable year. And so we're going to set our key to be the year, and the value, which is the values inside of here. These represent the cases, and so value is case. This is going to take all of those columns, gather those together into two columns. P is going to be the year, and that contains what was our column names, and the value contains what was our values. So you can see why that one's the more intuitive one. That's going to create this cases column here. And so we could do a similar thing using table B. Rather than cases, we would have population, because that's what that table contained. See later how we could combine those two together, kind of adding the cases and population column together to get back to table 1, the tidy format. Okay, and visually, this is what happened here. We took 1999, 2000, and gathered them together into these two columns. You can imagine if we had way more columns here, maybe 10 of them, we'll gather them together into two columns, just have more repeats of the same country. Okay, and so we'll now look at this thing called spreading, and this is going to help us deal with the issue we had with table 2. Table 2 looks something like this. So this kind of suffers from the opposite problem of last time. So here, a single observation, which is a country in a given year, rather than being having two observations in one row, we now have one observation split across two rows. So information on Afghanistan in 1999 contained in this row and this row. And because of that, we have this non-variable column here, which is type. Type isn't something you can measure about a country in a given year. And so we want to resolve this and get this back to looking like table 1. And so we can do this using a thing called spreading. And it's kind of, well, it is in fact the opposite of gathering. So here we have these two columns, type and its count. And what we want to do is spread out this, this type into two columns. So one column for cases and one for population, and fill in the values. And you can imagine if we have multiple things here, so cases, population, GDP, I don't know, mortality rate, various different things like that. We have loads of things here, and then we're spreading them all out into multiple different columns here. So that's where the name spread comes from. And we're going to use very similar arguments to the last time. We only need 2 parameters this time. It's clear. Okay, yeah, let's explain it first. So the 2 parameters we're going to need is the name of our key column. So that's the one that's going to get transformed into the column names. That's our type column here. And we're going to need a value column which contains the actual values. And as before, the value one's a more intuitive one because clearly these are values of a certain variable. So I set value equal to count, and then key must be the other one. Bit hard to remember, but that's the kind of rule of thumb that I use. So we specify that those 2, and then those will automatically get spread out into those columns. You don't have to specify a 3rd parameter like we did with gather. So we can use spread. We can take table 2, type it into the spread function, specify that our key was this type column and our value is this count column. And notice we don't have to use quotes here. We did with gather. And the reason for that is that with gather, we were creating columns that didn't already exist. We had to use quotes to let R know, we're not talking about variables here. We mean these this text data. But here, because these columns already exist in our data set, R can recognize that, and we don't need those quotes. You can see here, this takes those 2 columns and spreads them out into the columns cases and population. And we're actually right back at table 2 here. Sorry, at table 1. And so as mentioned, we don't need the quotes for this one. So visually, something like this. We're kind of taking all these different observations, or sorry, all these rows for the same observation, and spreading them out into multiple columns. You can imagine if we have cases, population, GDP, education, various things, that would all be spread out into these multiple columns here. That's where the name comes from. Okay, so as you can probably guess, just how they act and the common argument names, key and value, spread and gather are in fact opposites of each other and can be used to reverse the effects of one another. And so gathering takes a very wide data set and makes it narrow. So we saw when we had those columns, 1999, 2000, there could be more of those, 2001, 2, 3, 4, 5. That's a very wide data set. And then we gathered together all those columns into two columns, the key and the value, which was year and cases, making it narrow but longer. Spread does the opposite. It takes a very tall data set and makes it shorter and wider. For example, if we had multiple rows for cases, population, various other things, those then get spread out into their own columns, making it a lot wider. And so collectively, these operations are known as pivoting. You might recognize these from pivot tables in Excel. And so the general rule of thumb is that wide tables, like the one with all the years, 1999, 2000, up to whatever, those are good for looking at data because our field of vision is wide. We see things with a rectangle in that in landscape mode, I guess. And so having these wide tables is better for a human, but it's not very efficient for analysis. Faster, it's easier, just more efficient in general to do analysis on tall data, or specifically on tidy data. And so you'll often get data given to you in a wide format, but want to convert it into a tall one. And when you're outputting things as a final product, you might want to convert it back into wide because it's easier for humans to interpret that. Okay, so I'm also going to mention this thing called pivoting. And I'll link to this in the description of this video. We'll pop it in the chat in the hybrid live sessions. So since TidyR version 1.0, which was September 2019, there's been a new syntax for pivoting tables that's been added. And so this gives two new functions, pivot longer and pivot wider, which respectively replace gather and spread. And the idea is they're meant to be a more intuitive syntax with more powerful features. As of the time that I made this presentation, and as of the time of recording, these functions are still in an experimental stage of their life cycle. And in TidyR 1.1, they'll be moving into maturing. And so, even though these are very stable, you're free to use them in your own work, and you won't run into any issues. Their syntax might change a bit in new versions. And also the bigger issue is that a lot of legacy code, so old examples and existing things, is written using the older syntax. And so I decided to teach in this course the older syntax so you know it. And then if you want to learn more about pivoting, or pivot longer, pivot wider, this new, more elegant syntax, well, then you're free to learn that, but at least you'll know the legacy thing if you ever come across that. But yeah, you're completely fine using pivot longer, pivot wider for everything, as long as it's not something that has to be stable forever. There might be changes in the future until it comes out of experimental and maturing into stable. Okay, so let's now talk about some other ways we can handle non-tidy data, those other tables that we looked at the start. First, we're going to look at this thing called separating. So let's have a look at table 3 now. So something like this, and kind of getting the gist of what tidy data is, it should be clear this is not tidy data. Why? Well, two reasons. It's impossible to have one reason. So this violates the last rule, tidy data, and also the first at the same time. The last rule is the clearest one that's violated, which is that every value has to have its own cell. So every number or every kind of piece of data should be in its own cell. Here we have a cell here with two values, cases and the population. And so this then gives us the problem that we have this non-variable column rate. The rate, even though I guess, yes, we can measure the rate about, so the rate of infections, the cases per population for a country, is not something we care about. Like, we don't care about the rate directly. We care about the cases and the cases and the population. If we only cared about the rate itself and you weren't interested in that more kind of nuanced view of things, then yeah, rate would be a reasonable variable. Although we'd want to store it as the actual decimal value rather than this character string being the two numbers and a slash. So I guess this is a good time to mention that tidy data is subjective. And well, guys, no, it's objective, but it depends on your context. So what determines whether data is tidy depends on what you're trying to do with that data. And so if we care about the rate as our main indicator, then having this numeric version of this would be tidy. Since we care about the cases and the population, this is not a tidy format. What we're going to want to do is separate these out into the cases and population column. So we can do that using the separate function. and it does what it says on the tin, separates them out into 2 columns. So we have to specify 2 parameters. The first is the column that we want to split, and then we also have to specify the names of the new columns we're going to create. And then so by default, separate's going to split the values in the column we specify whenever it sees a character that is non-alphanumeric, so not a letter or a number. Although we can manually specify which character to split on using the optional sep argument. And sometimes it's good to just throw this in for safety. Maybe for some reason, a data processing error, you had a negative case rate. It was like minus 7445. If you were separating at all non-numeric or non-alphanumeric values, we would separate before the dash. The number here would be one value, then slash, then another value. So we'd have 3 values separated here, and 2 in the rest of them. It's all going to break down. So sometimes it's safest to specify manually what column we're separating on, so we don't run into any issues. We also will likely want to specify convert equals true, and that will let tidyr automatically convert the new columns to their correct types. As we can see here, it's being stored as characters, as text data, because we have a slash in it. And for that reason, if we separated these, we'd get characters back. Convert will use a heuristic to look at them and guess what the correct type is, and then convert them into that type. Looking at this in practice, we have something like this. So table 3, put it into separate, and then the column we're separating is the rate column. And we can specify into equals and then a character vector giving the names of the new columns we're creating. I manually specify the separator to be a slash and set convert equals to true to turn these into integers, otherwise they would be characters. And so a bonus note that we'll look at in the homework, separate can also contain a vector, can use a vector of integers as the sep argument, which will kind of say exactly where to split things. Maybe there is no separating character. Say if you have the time in military time, you want to extract the hours and the minutes, then there's no separating character, but you know that the first 2 are the hours, the second 2 are the minutes. And so you could specify using numbers what that is. But we'll see that in the homework, or you can look at the documentation, question mark, separate. And diagramming this, we have something like this, taking this single column and separating it, as the name suggests, into these 2 columns here. Okay, and then unsurprisingly, there is an opposite of this, or kind of a reversing function, and this is known as uniting. So taking multiple columns and uniting them together into a single column. And so we're going to look at a table we haven't seen so far, table 5 here, and this is just a disaster, really, a disaster of data processing. But you do get data like this in reality, so it's good to know how to handle this. And in this case, we had century and year split out into their own columns, and so this violates again the last rule of Tidydata, which is that every value should be in its own cell. Because now a single value, the year, is in 2 cells. And we end up with these non-variable columns, century and year. And again, it's worth mentioning kind of that the nature of Tidydata is based on the context, kind of what questions we're asking. If we cared about century and year independently, then this would be fine. But what we care about is the actual year itself. We don't, the century doesn't really matter. It's not a variable of interest. And so we would be better having these as a single column. And so we have these split up. Let's combine them together using unite. To do that, we'll have to specify 2 things. One is the name of the new column to create. I think we'll need to specify 3 things. Yeah, we'll need to specify which columns to combine together, and then the name of the new column to create. Oh yeah, sorry, that was the second thing. So yeah, we need to specify the name of the new column to create and the set of columns to combine together to make that new one. And then optionally, we can also include a sep argument. We're going to say what to separate these by when we combine them. Otherwise, we'll use an underscore by default. So by default, if we combine these together, we'd get 19 underscore 99, but we can overwrite that using sep. So looking at this in practice, we use table 5 piped into unite. first thing is the new column to create. We're going to call this new. So it would have made more sense to call this year, because I mean that's the column we're creating is a year column. But I avoided doing that because it would be confusing. This was year before, it wouldn't be clear what was happening there. So we've called this this new for now. And so we united these together. We could have called this new, but I called it could have called it year, but I called it new. And then we take century and year and combine those together or unite them together with a separator of a space. And so whenever we use unite, it does not have a convert parameter. And actually, it will always give you a result as a character. The reason is that the separating character is a character, so for consistency, it always returns a character. And so we could use mutate with the function as integer, convert this into an integer. Just have an example of this. Let's load up Tidyverse, little script to write this code in. We'll take table 5, and then from this, so if we run this first bit of code here, get this output here, and what we can do, we can mutate and set, well actually no, let's call this year just to prove that we can do that. But then we can set year to be as.integer of year. We're overwriting the year column with the integer version of itself. So here it's a character. We run this now, and we get an integer. And then we could use separate as we did before to turn rate into 2 columns, and we're back to table 1, the tidy format. And diagramming that, we have something like this, as we would expect. Okay, so that's all for tidy data. We're now going to have a look at this thing called relational data. So let's introduce that. Well, first, where are we? So we're now back in transformation. I guess really we're in some kind of like gray area between tidying and transforming. Yeah, somewhere there, but yeah, it doesn't really matter exactly. The important thing is we're using dplyr to do this. So dplyr is more associated with transforming data. So let's say we're there. Why not? And so the motivation for this is that often when we're doing data analysis or data science, it's rarely going to be the case that we are only concerned with a single table of data. We might want to combine data together from multiple sources, so get some GDP data, cross-correlate that with education, maybe throw in some demographic information, bring those all together to do a more powerful analysis. And so we need to know how to take multiple data sets and combine them together into one. And we can do that using dplyr. Let's talk about relationships, and not the standard type of relationships between data. And so relations are defined between pairs of tables. They basically describe how two bits of data, two tables of data are related. And so this is maybe a strange idea. So you may think that GDP, education, and demographic information are all related to each other. Like there's a triangle of relation there. But I guess the way we should think about that is actually we can break those down into pairs of relationships. I guess even with a triangle is all related together. But if you think about it, actually all we have are those 3 lines showing the pairs of relations. And so that's how we kind of build up relations of data, that we consider how 2 things are related, then ask how one of those is related to another, and then we build that all up into a whole network of relations. So that's the idea here, that the relations of 3 or more tables, they're always a property of the relations between the pairs of the individual pairs. So yeah, that's kind of a bit philosophical. We'll come back to that a bit more later. And so the important point is that there's loads of different types of relations you can have between data or between tables. But due to time constraints, teaching everything in 5 sessions, we're not going to cover all of those. We're only going to look at a specific type of relation known as mutating joins. And these are the most important type of joins that allow us to take 2 data sets and kind of merge them together into one. There's 2 other types of joins or kind of relational operations. Those are filtering joins and set operations. If you want to learn more about these, chapter 10 of R for Data Science, available freely on the web, linked in the first session. You can have a look at that. These might be handy for when we have the data visualization competition at the end of this course, if you're doing one of the hybrid live versions. Okay, so let's look at mutating joins. So a mutating join allows us to combine together variables, two tables, take two tables, combine them together into a single one. And so this is performed by matching observations based on a collection of columns, maybe a single column. And we refer to this as the key. So we have two columns, we have two tables, and we have the key in both of those. We match up where the keys have the same value, and then use that to share values from each tables across a single observation. And so many different types of these mutating joins, and they differ in how they handle missing values. But there's a common thread between all those, and that's they take three main arguments. So the two tables that are going to be joined together, and then either a single column or a character vector of column names going to be used as the key, so the columns that we join on. The output is always the same. It is a single table containing the shared keys and then any variables that were found in both tables. And so, looking at this, we can see that we're going to learn how to join together two tables, then linking back to this idea about the philosophy of pairwise relations. If we want to join together three tables, we can do that by joining together two and joining on the third one to the newly formed combination of the first two. So we can just do these pairwise. Okay, so to look at mutating joins, we're going to use these kind of toy data sets known as band members and band instruments. These contain information about the Beatles and the Rolling Stones, the members of the band, Mick Jagger, John Lennon, Paul McCartney, Stones and Beatles, and then the instruments that certain ones of these artists play. So John on guitar, Paul on bass, etc. Okay, so let's have a look at how we can do a simple join. So the inner join is the simplest type of join. And so this matches together observations based on a key, whenever the key is equal. The rule of an inner join is that it only is going to keep rows that appear in both tables. So basically just not going to even consider missing values. It just gets about those, only joins together things that exist in both tables. And so the output, as we mentioned, is going to be another table containing all the variables of interest, but only for rows that appear in both, only for keys, in fact, that appear in both tables. Let's have a look at this. Let's go over into the console. So we have band members here and band instruments, and we're going to join these together. Let's make this a bit bigger. So we're going to use inner underscore join to do an inner join, and we're joining together band members and band instruments. And then the key we specify using this by argument or parameter. And so we're setting by equal to name. So we're joining them together using the column name. You can see we have name in both of these data sets. It's kind of the thing that ties these two things together. And so we do that join, and we end up with something like this. Notice this only contains two rows, one for John and one for Paul. And the reason for this is that even though we have Keith in this data set, Keith doesn't appear in the band members data set. And even though we have Mick in the band members, doesn't appear in band instruments. And so because of that, we only keep John and Paul because they appear in both data sets. That's kind of the rule of an inner join, only keep things that appear in both places. The most ruthless of joins. Okay, so relaxing things a bit, let's have a look at the left join. And so it's very similar to the inner join, but we'll handle missing values with a bit more tolerance. The idea of a left join is that, well, first let's look at this. Whenever we do a join, we put in two tables, and the one we put in first is known as the left one on the right is known as the right one. So the one on the left is the left one, unsurprisingly. And then what a left join is going to do is going to preserve any key that appears in the left table. Basically, it gives precedence to the left table and will fill any missing values using NA. For example, we do left join with band members and band instruments. Let's do this down in the console. So we do a left join, and so this is going to give precedence to anything in band members because that's the left data set. The final thing is going to have keys for Mick, John, and Paul. because we're focusing on the left data set here. There we go, we have Mick, John, and Paul. John and Paul, we could find them in the instruments, so we have this plays column, but we couldn't find Mick, and so we just fill this with an NA. And Keith, well, Keith's in the right table, we don't care. It wasn't in the left table, and the left join focuses on the left. We're left with a missing value here for Mick. Not a problem, it's just saying we didn't have information about what instrument Mick played. Okay, and then similarly we have a right join. This is the opposite of a left join. It gives precedence to the right-hand table. And so, for example here, we do the exact same ones as before, the same tables, but now rather than having a missing value for Mick, we keep Keith, who appeared in the band Instruments, and have a missing value for what band he was a member of. So it's the opposite of the left join. And so you may be asking, well, what's the point of a left join and a right join? Surely I could just use a left join but reverse the order of these. And so then that would be the same as doing a right join in this order. And the reason we have both of them is for piping. If you remember with piping, that it puts the output of the previous command into the first argument. And so sometimes we don't have the option to flip the order. When we're doing piping, we always have our current data set we're working on going into the first position. That's why we have left and right join. Sometimes one will be more convenient than the other. So finally, we look at a full join, and this kind of combines together the behavior of a left join and right join. It's the most flexible of all joins, and just says keep everything. So if a key appears in the left table or the right table, basically if a key exists, it will appear in the final thing. And because of this, we'll get NAs in both columns, or we can get NAs in both columns, or it's just that. So we end up with 4 rows here. Mick, we didn't know what he played. He wasn't in band instruments. We get an NA here. And Keith, he wasn't in band members. We don't know what band he was in. So just these 2 missing values here. And so it's more flexible. And so I guess final point I'll mention is kind of choosing between these. When is it best to use each type? And it comes down to often how kind of robust and secure you want to be with your analysis. Sometimes you're doing a quick, dirty analysis, you don't care, just use an inner join. There might be some missing values, who cares? It's not a big deal. It's better not running into any errors from having missing values in your code. For quick, dirty things, inner joins are best. And for a full join, or kind of left or right, those are more useful when you're making more robust code. You want to guarantee that missing values aren't there. If you could use a full join, for example, and then do a check, maybe using filter, to assert or guarantee that there's no missing values, and then that would be a way of checking that everything matched up perfectly. But with an inner join, you'd never get those missing values. You'd never be able to even check that. So it all comes down to how robust you want to be, and in certain times it will make sense when actually you have to use one over the other. And we'll give some examples in the hybrid live sessions of why and when that matters. So moving on, what can we do if we have 2 keys, well, one for each table, that have different names? They mean the same thing, but have different names. So dplyr can handle this just fine. We just have to make a slight modification. And so we're going to use a dataset called band instruments. It is exactly the same as band instruments 2, which is the same as band instruments itself. Rather than having the name we have for this, rather than name, we have artist. So the same data, but now we're joining with different names here. So name connect with artist. How do we handle this? Well, rather than using just a single value or a vector of keys, of kind of column names to use as our keys, we instead use what's called a named vector. And we can create it using this syntax here. So we take, let's do an inner join, for example, on band members and band instrument 2. And then rather than just setting it equal to name, quotes, we use C to create a vector. And then we create a named vector using this syntax here, where we have the name of the column in the left-hand table is equal to the name of the column in the right-hand table. So here, band members uses name, which is the left one, and band instruments, the right one, is artist. We set that name equal to artist. And then those will be combined together, and we'll use the left-hand one as the name in the final table. And what if we have duplicate keys? So mutation joins will handle this fine, and often this is a very useful feature of joins, and it's actually our intention in the first place. And so, detailed discussion of this is beyond the scope. But here's a brief example, and then maybe just mess around more yourself, kind of learn exactly how this works, or look at R for data science for even more detail. Let's break this down bit by bit. So let's put this in a script over here. So I create two data sets here. I have employees and then sales. So John and Anne, they've worked for 4 and 7 years. And then we have different item codes and who they were sold by. And so we might want to reasonably join these together. We can do this using an inner join, so on employees. So sales goes into the first thing here. So in sales to employees, by sold by is the name in sales, and name is the name in employees. We join those together, and we'll see that we end up with 3 rows here. Even though there's only 2 rows in the original here, we end up with 3 in the final thing. That's because we matched up each pair. So we went, John matches to John, so we matched the 21. That works fine. But Anne has 2 sales, and so we match first this row to here, and then we duplicate that and match the second one. If we had multiple instances of Anne, those would all get matched together. And so I guess now you can see the benefit of having data stored across multiple different tables rather than in one massive table. Because by joining here, we create a duplication. We now store Anne's experience twice. So this data here, it represents the exact same thing as these 2 tables. We duplicated data now. So now issues could arise. Maybe if Anne, we changed her experience, she worked an extra year. We have to remember to change this in both places here. And if there was loads of instances of this, if Anne had solved many different things, that might get messy. And so we often store things in different tables and combine them together temporarily for analysis, but leave the raw format like this. That's the motivation to why we use joins and relational data. Okay, and so how could we create this graph? I was not expecting this, but let's have a look at doing this. So let's go at full screen, and actually let's work on making this graph together now. Okay, this. Okay, so let's make this graph from scratch. So we're using the mile per gallon data set here. So what do we have? It's fairly small, sorry. We have for each class of various cars, we want to know what their city and highway mileage are compared to each other. Okay, and we want a column chart of this. Okay, so I guess this is quite a good example, especially that it threw me. You'll see actually what it looks like working through this process. So we're going to start with a mile per gallon data set. That's no surprise. And I'm going to start by filtering this down, or selecting down, just to the columns that we care about. So we're going to need, what do we have? The mileages, the class. Okay, so we're just going to need class, city mileage, and the highway mileage. I'm doing this, it's not necessary, just so we have a bit of a smaller format here, just to look at. Okay, so wanting to calculate average mileage each of the city and highway mileages. Okay. We're going to do that. We're going to want to be able to group by whether this data is city or highway. But to group by a variable, we need to have those values contained in a column. Currently, we have city and highway as their own columns. So here's an interesting point. Even though the mile per gallon data set is in tidy format, they wouldn't include that in the base Tidyverse if it wasn't in tidy format. It's not tidy for this question. Tidy for most purposes, but for this context here, actually there is a different tidy format. And that's going to involve gathering together these 2 columns into a column for the type of mileage and what the mileage was itself. We can use gather to do that. So we're going to bring together the city and the highway column. The key, which is going to be kind of the variable representing these, are now going to be considered values. They were variables before. In this new context, they're considered to be values. So that's going to be, I guess we'll call it type. It's the type of mileage. And then the value is going to be these things in here. Well, that's the mileage itself. I guess another way that we could have thought about why we had to do this is that in ggplot, we map variables to aesthetics. And we can see here that our fill aesthetic, blue or red, is the mileage type. That wasn't a variable in our initial data set, so we're going to have to create a column containing the type of mileage. And so we run this, and now we can see, oh yeah, okay, we have a column there. Full type is the type of mileage. Our y-axis here is the average mileage. Well, we can see we have a column here for mileage. Before we had mileage split across two different things, so we're looking good here. Okay, so the next step is going to be figure out what these average mileages are. So we're going to need to group by, and we'll group by each city. No, sorry, by each type, because we want one for the city, one for the highway. And now we can do a summarize to collapse these mileages down to their mean. Wait, sorry, no. We want each of these bars is the average mileage for each type and each class. We're going to group by both the class and the type. And then we're going to summarize, let's call this average underscore mileage. It's going to be the mean of the mileage column. Yeah, okay. So we're going to run that. Let's see where we are at this point. Yeah, so now we have each type, class, what is the average mileage? We're looking good here. I think we're ready to plot things now. So let's do ggplot. So we're piping in our data. Our aesthetics are going to be x is the class, y is the average mileage, and then fill is going to be the type. And let's add geom col, creating a column plot. We'll learn more about this in next session. We run this and we get something like this. So it's close to what we were after. Turns out we're missing a thing called position equals dodge. And we'll explain what this means in next session. Basically here they're currently stacked, the position is stacking. We want to dodge them side by side, something like this. So you can see the theming is a bit different, it's not quite as pretty, but the general idea is there. We'll learn next session how we can theme this and style it to make it look exactly the same as this plot here. That's kind of, a very practical and a practical example of what using IDR and dplyr together, ggplot as well, looks like. It's actually, this is a good example of combining together all the bits of the tidyverse we've seen so far. And so, yeah, the most complicated step was figuring out that we needed to gather our data. And this will come with experience. And I guess the way we could have arrived at this was to try making this ggplot and realizing we couldn't do it. And at that point we go, okay, it's really difficult to make a ggplot with the current MPG. It must not be tidy for this context. How can we manipulate it to make it so? You can try gathering, try spreading, try various things, and soon you'll figure that actually gathering was the one you wanted. And I gave a few hints at the reasons going on in my head while I was giving the example. So with that, that's the end of today's session. I look forward to you joining again next week, where we'll learn more about advanced visualization and wrap up the course. See you then.